save the crossword for later, because now we're going to do math. So pattern blocks are extremely widespread in K6, less so in middle school and high school. And I'm going to present some stuff that's appropriate for middle school and high school that you can do with these. And the first thing you should do is, open the boxes and find a way to share these with all your neighbors. So including them. Yeah, and I have more here. I just need some to have up here, but there's more. Some area need these. Okay. Okay, so just start by just getting acquainted with what you have. Most of the activities we're going to do are from this book, which is out of print but available as a free download on my website. And in fact, all the handouts that you're going to get today are easily downloadable. I'll show you where. So, okay, we'll start with a couple of puzzles. Make a red triangle and find the area of the tan block. So this is the one whose area I'm asking about. Is this showing up? Yeah, what's the area of this? And my hint is you don't need to do any calculations. You need to arrange blocks in a meaningful way that will reveal the area. All the edges are 1 inch, except for the long edge of the trapezoid, which is 2 inches. And I'm asking for the area of the tan block. I'm going to mostly follow the way it's done in elementary school and call the blocks by their color. So this is the tan block. This is the area we're looking for.
Do you know the sides of the tan block?
Yeah. 1 inch. The sides are 1 inch. All the sides of all the blocks are 1 inch. We have an answer. Okay, and so the area, figure it. No, don't say. So what Paul did is he made a design with a few blocks, and then the same design above it, or on top of it, and then knowing that, he was able to figure out the area. That's it, right, exactly. You were cutting off a little above the... Yeah. And I'm ready to give another hint, if you want. Okay, my second hint is it only takes 3 blocks. And then 3 other blocks on top of those.
What is the first block? Is this one of the blocks?
No. maybe I'll give another hint. So a lot of people have two tan blocks arranged this way. That's pretty much the key to the whole thing. Okay, now make that same shape another way. All right. Should I give it away? Oh yeah. You're gonna need those orange ones. Yeah. All right. So, should I reveal the answer? No. Okay. So you can do this shape this way, but the exact same shape this way. And so this has to be half of that. So the area is 1/2. Wait. I'm not sure what you're saying. Which height are we talking about? Well, this one is easier to understand because you don't have to know anything. but that's correct. Okay, so yeah, because you can see that if you take the height from here, so it's just not as obvious to most of us. Okay, here's your next challenge: convex polygons with all different numbers of sides. So for example, a triangle, that's a convex polygon. Well, basically, what you want, you don't want any inside angles to be greater than 180. So triangle is already made, a square is already made, and a pentagon we just had. So these are pentagons, 1, 2, 3, 4, 5 sides. So we already have a convex triangle, square, and pentagon. And hexagon we get for free as well. So now try and make a 7-gon, 8-gon, 9-gon, and so on that are convex. So this would not be allowed because not convex. No. It can't be regular, mostly. So see how you do. Oh yeah, that was good. Oh no, it doesn't quite close it. So we're looking for 7-gon and let's see. No, that's a pentagon.
This is 7. 2. 2 is 4.
No, I'm not talking about the perimeter. I'm talking about how many sides. That's one side.
Okay.
So that's 4 sides. Okay, so 1, 2, 3, 4, 5, 6. So that's a hexagon, 6-sided. I want 7 and more. Because for the hexagon, we already had this one. Yeah. Oh. No, that's no going in.
So we're trying to build, we've already built, trying to build a 7 gun with no convex.
And don't limit yourself to a 7 gun. You can go an 8 gun, 9 gun, whatever, however many, just more than 6. Man, I started you with a hard problem this morning. Oh, you have a 7 gun? Let's see. 1, 2, 3, 4, 5, 6, 7. Well, there probably is a simpler one, but if nobody comes up with a simpler one, I'm going to ask you to show this one. No, these are not convex.
Oh, they're not.
No, to be convex, you can't see how this goes in.
Oh,
So to be convex, they all have to. None of the angles can be that big. See,
Right.
so when you have this angle is more than 180, and so see if you put this in here,
oh, okay, I got it.
then that's this. Now it's convex on this side, but not on that side. So do you see what I mean by convex? You
Yes.
can't go
I was looking
inward.
at the-
So we're counting the sides. So this would be 1, 2, 3. We're not doing perimeter. We're doing how many sides does it have?
Okay.
So it has 1, 2, 3, 4, 5, 6. Whoops.
So it's okay.
So that's a six-sided. One, 2, 3, 4, 5, 6, 7. Okay. Can I show this? Okay. Peter found a 7 gun. So is this 7? So 1, 2, 3, 4, 5, 6, 7. Okay, and then we have a 9. No, that's not convex. So 9 gone, convex, 12 gone. See the hexagon in the middle, and then so there's 6 sides times 2. So it's a nice dodecagon. We will return to the dodecagon in a bit. Okay, so I'm going to show you the activity that I do on day 1 of a geometry class. So the idea is you draw a point on a piece of paper, and then you surround it with pattern block angles. And you keep track on the sheet that you just got of what you've accomplished, like which ones were, I should get one of those sheets. When you've succeeded in doing one, you circle it. If you're convinced one is impossible, you cross it out, and so on. So let me switch again then. So for example, this is 2 colors, blue and red, and 3 blocks. So that one is already circled on your paper. if you had done, well, let me switch. So first of all, here's our 11. For some reason, the colors are not clear, but there it is. That's the 11. Maybe it's because of the black background. That's weird. Anyway, and so let's say this is my point, and I surround it with squares like this. Then I've done all orange. So on my chart, this would be all orange, and I would circle 4 because it took four blocks. And this is not legitimate. You have to have a vertex on the point. This would not count. So let's talk about it a little bit. First of all, did you find any that were impossible? Okay, so raise your hand and tell us something that's impossible and why you know it's impossible. So but what if you add up all the angles, you got more than 360, but did you choose the right angles to add? Oh, yeah. So if you pick the smallest angle in each color and add them up, it's more than 360. So 6 color isn't going to work. Well, then why was it on the sheet? Why was it on the sheet? To stretch your brain, to generate exactly that proof. And what else wasn't on the sheet? Yeah, all the single colors stop at 6, and yet, did somebody find one color? Okay, what did you find? Yeah, the 10, you can do 12 by using the small angle all the way around. Or 8, in fact, because you start with the 12. How did you get the 8? Yeah, you can replace 5 of the small angle with one of the larger angles. So point I'm trying to make day 1 of my geometry class is, in math, what's correct, it's not necessarily what's on the paper. It's not necessarily what the teacher says. It has to be determined by logic. And so here you defeated my sheet by pointing out its logical flaws with excellent arguments. Also, if you had read the instructions, you would have seen that you could add your own numbers and circle them. Another message I want to give on day 1. Okay, so for the green, what did you circle for all green? Yeah, can somebody explain why for all green there was only one thing you could do? Go ahead. Yeah, exactly. All the angles are equal, so there are no choices. So which other blocks besides the green have that property? Yeah, the square, there's only one way to do it. And likewise the hexagon. Okay, tell me a couple more impossible things. So 6s were all impossible. What else is impossible? Yeah, you couldn't get 5 colors from 3 or 4 blocks. Right.
And if you have the 5 color, you need the orange, which is 90. And the smallest you can do on the red, blue, and green, which are each 60, which leaves you only space for 3 more 30. So I think the most you can do with 5 colors is 7.
Do people agree with that?
Yeah. So probably you can do 5, 6, and 7. You can't do 3,
Okay. So these are all good discussions to have at the beginning of a geometry class. Part of the reason for the activity is that I was a high school teacher, and I don't know if any of you have had this experience of trying to explain how to use a protractor. For some kids, that is just impenetrable, and that's because they don't know what an angle is. They don't know what they're measuring. And an activity like this, it forces them to think about angles. And all of you were talking in terms of degrees. Day one of my geometry class, even though it's a high school class, degrees don't come up very often. Mostly they say too big and too small about the angles, and which is actually what I want, because once you get this idea of surrounding a point with a bunch of angles, you sort of get at the essence of what we're talking about here. So it's good for a range of students, because for some students, they're just learning what an angle is. For other students, they're making these sophisticated logical arguments. So, okay, so that was angles around a point. So another thing pattern blocks are good for is an introduction to doing some work with symmetry. These have rotational symmetry, and these don't. Rotational symmetry is if you turn it, will you get back to the exact same position? So can you tell the difference between this one and this one? Explain it to your neighbor. Why do I say that this one does have rotational symmetry and this one doesn't? Tell your neighbors, don't tell me, I know.
So on all three arrows are sort of the same. Laterals are not
Oh, it's different. Oh, I see. It's bad difference.
Yeah, it's
Bad difference.
yeah.
Thinking two wings.
So
It's funny. It's
It's the same.
so this one it's under, over for each arrow. Under, over, under, over. Here we have under, over, whoops, over, under. So you have so this one, it's under, over for each arrow. Under, over, over. Here we have under, over, whoops, over, under. So you have to pay close attention. Anyway, so this has five fold. It's called, the word fold is unfortunate because it doesn't involve folding. But anyway, it's called five-fold rotational symmetry. So show me on your fingers. This is how many fold? No, on your fingers. Okay. We have some disagreements. So how many fold for this one? Somebody raise your hand and explain to the group if I pick you. Go ahead.
It's twofold because if you rotate 180 degree, the left wing will fall on right wing.
Right. So it's 180 degree rotation would do the job. That's twofold. What about this one? Same exact thing. Okay. And these don't have rotational symmetry, but several of them do have mirror symmetry or line symmetry. For example, this one, and this one. So, okay, so your task is going to be to make some symmetric tilings of these three shapes. So you have to cover these three shapes. Just choose one, cover it with blocks, and then record what kind of symmetry you had. Did you have line symmetry? Did you have... So let me show you some examples so you'll know what I'm talking about. Okay, look up just for a bit. So no plastic in your hands right now. Right, no plastic. So here's an example. Does this have line symmetry or mirror symmetry? Nope. No, the shape, counting the blocks. Yeah, the shape itself does, but counting the blocks, no. But it does have rotational symmetry. How many fold? Threefold. Okay. Now here, the same shape tiled differently. What about now? No symmetry at all. And then what about now? Line symmetry, but no rotational symmetry. And I was kind of mean because instead of the usual vertical line of symmetry, I made it go sideways. Okay, so that's what you're looking for. And so for each of these shapes, you would have put a check mark on your chart. So for the triangle, this would be no rotation, one line of symmetry. So so make some shapes, see what you get. So these are photos from my class. Well, I only took pictures of the good ones. No, actually, I took pictures of everything, but I'm only showing you the good ones. So, yeah, so I mean, I think this is often we talk about symmetry very briefly, but it's kind of an important and challenging thing for many people, and largely because of lack of experience. So this is a way to give people experience with symmetry. And I mean, as you saw, it's not straightforward, making these shapes. But it's very satisfying when you have a good one, as evidenced by people photographing their creations. Anyway, a good classroom activity. So we're back to pi, and I made a little animation to illustrate this. So I guess I need to sit here. So let's say we already know, we agree that pi is the number that works for the circumference. Circumference is 2 pi r. And but now we're interested in the area. So here's a pi, a circle, divided into 12 pieces, sectors. We can rearrange them so they look like this. But let's have more pieces. So it's all, you can, if you make the pieces small enough, it'll almost a rectangle. It's not really a rectangle because the top has little bumps, and the angles are not exactly 90, but it's very close to a rectangle, and we can get as close as we want by just doing more pieces. So what are the dimensions of this rectangle? Maybe it's easier to think about if I go to fewer pieces. So remember how I made it. So remember how I made it. So how long is this?
1 inch by 3.1.
So this is my original radius, or very close to it. Oh no, in fact, it is. My original radius is the angle that's very close. So this is my radius. But how long is this? Yeah, well, the circumference is the top and the bottom, right?
Okay, so, yeah, because it's so 2 pi r, so it's just 1 pi r.
It's exactly, it's just 1 pi r. So approximately r, approximately pi r, so this makes it plausible. It's not totally rigorous as a proof, but close enough for school. And it makes it plausible that pi r squared actually will work for a circle. So I won't tell you how long it takes to make these things. But anyway, but it's satisfying when you're done. But of course, this is a pattern block activities day, and that brings up the question: well, is there a pi? Notice the quotation marks. So this is we're not no longer talking about the real pi. We're talking about pi. Is there a pi for regular polygons? So, for example, a square. Let's say this was the radius. What would be the perimeter of this square? No. The radius is r. This length is r. So if this is r, this is r times square root of 2, and there's 4 of them, which is 2 times 2 of them. So you can think of, if there was a pi for squares for perimeter, it would be 2 square roots of 2. Not okay, not impressive, especially since for area, if it was pi r squared, it's actually 2, because what you can see that this triangle has area 1/2 of r squared, and we have 4 of them. So it's 2r squared. So the pi for area would be 2. So it's not the same pi. So a square must not be a circle. So we have now established this. But how about hexagon? Wait, what? Come back? Oh, yeah.
So if you instead of cutting it like this, if you cut it like this,
Yeah.
it's a different radius, then it does work.
Okay, so if we made the radius be this,
Yeah.
then, okay, so then the perimeter would be 1, 2, no, it would be 2, 4, 6, 8. So pi would be 4 for perimeter. And what would it be for area? So it would be so with this radius it would work. Oh, cool. Okay. Unfortunately, it's not as good a setup for my next question. No, that's great. I never thought of it that way, but that's great. So use your pattern blocks to figure out the perimeter pi for a hexagon, for a regular hexagon. So this can be easily done with the pattern blocks. Just cover it with triangles. And so what would be pi for this?
Usually the diameter is defined as the biggest distance between the vertices. So this definition.
Yeah, so for a hexagon, perimeter pi is 3, because 2 times 3, times the radius. Okay, but now watch this. So this is only for perimeter. We're not going to do the area one. But now watch this. This is the shape that we've seen a few times today. And we're going to do an area pi for the dodecagon. And I'm going to give you a picture that will help you think about it. So your job is, what's the area of the dodecagon in terms of the radius, this being the radius. And my hint is that on the paper I gave you, this can be figured out by paying close attention to the picture. And this can't actually be done with blocks, even though it's a block-based, pattern block-based design. It's you need the printed picture to figure it out. Yeah.
So we already figured out the area of the.
Uh-huh.
Of the text.
Well,
Then we get the area of the
if this is
Almost.
These
Yeah,
are-
well, but you still have those triangles to deal
we
with.
just need to subtract off
Those are holes.
one
So this is the
triangle
little
and
dotted square.
one of the skinny pieces times 4, right? Because there's this is r squared, right? So it's 4r squared, but we got too much. We got 4 extras of these and 4 extras of those, and we need to account for and that there are how many of each of these here? There's 12 or 12 each. So that means I've got 1/3 too much. So it would be 12.
This is a quarter of.
No,
This is a quarter of the whole.
Yeah.
So we figured that they'd add up to 6.
Oh no, but these are not one unit. If this is a half, these are not one. The area of this is half of the square. But the square doesn't. The square doesn't have the same area as a triangle.
Yeah. Oh, okay, got it. Got it.
But where you're right is that that's how to figure it out, is by combining these pieces. Seeing.
Giving a value to them.
Well, you don't have to give them a value. You can just see how many you have and see how they connect. What do we have inside this dodecagon? But then we have to. This whole thing would be r squared.
Yeah.
So we have to remove these extras. So the question is how. So Paul had a very eloquent explanation that led to pi equals 3, and so here is how you can see it kind of visually here. You have to look because it's going to go fast.
How long did it take you to do that?
So the area is 3r squared. So if there was a pi for the area of a dodecagon, it would be 3. Now, remember, pi for the perimeter of a hexagon was also 3. Coincidence? No. I think not. When you have time, work the back of the sheet, which requires some basic trig, and there's an interesting pattern. So this tessellation, this tiling, was I'm told, proposed by a mathematician named Kershak in 1898 for this purpose. And and I can give you like a journal reference. It's in the back of my book here. He created this picture, and made this argument about the area of a dodecagon. So this lead, and so this is the tiling, and it takes us to our next topic. I'm going to give you some blank paper and some templates. So I need help passing things out. So okay, great. Basically, you're going to use this template to do tiling, to tile the plane. I think that, well, let's see if there's enough. Thanks. So, and here's, oh, sorry. So choose a triangle on the template different from your neighbors, and yeah, it's coming, but we can have it come from both sides. Because, well, you know, it depends on how many tilings you make, but we have extra paper if needed. So basically, what you want to do is choose a triangle, and use it as a tile, and find a way to tile the plane with your triangle. So, for example, here's a beginning of a tiling. Is this showing up? So the question is, which triangles work and which ones don't?
Does it have to line up with the edge of the paper?
No. Imagine the paper is infinite. And some triangles obviously are easier to work with than others. So
Are these two this is scalene, right?
yeah, I think so. Yeah.
All right.
Yeah, I think acute scalene and obtuse scalene. Oh, yeah, that'll work. So you can keep going with that pattern. A triangle. This is not a triangle. No one listens to me. Yeah. So a half square, you know, isosceles right triangle obviously is going to work. So if you want to try a more challenging one, like a scalene triangle, go for it.
The triangle one, the scaling one should not work though, right?
Try the scalene ones. When to stop? Is yours a scalene triangle?
Yes.
Okay, make it a little bigger, and then I'll use that to talk about this. No, same one. Just extend it.
Oh, make it bigger. Okay.
So here's another tiling. Again, a scalene triangle. So let's say this is early in a geometry class, or any time in middle school. It doesn't have to be a geometry class. What are some things that we can see in this picture? What are some ideas from math that we can see in this picture? Don't be shy. There's lots of ideas. If you have if you see something mathematical to say about this, raise your hand. Yeah, go ahead.
We see some translation.
So yeah, so one thing you can see is geometric transformation. So this is translated to here, translated to there, translated to there. We'll get half the triangles just by translating an original one. Okay, other things you see.
The angles of a triangle add up to 180, and so there's 6 of them round circles, using 2 of each.
So angle 1, let's say, angle 2, and angle 3. And the way we made this, we know that this also is angle 2, and this also is angle 3. And so they add up to 180 degrees, and twice them adds up to 360 degrees, going all around the point. Okay? Sum of the angles in a triangle. What else do we see? Sorry?
Florida. One, two, three.
Oh, so how how the numbers are organized. So 1, 2, 3. So and I should have come with color because if you color them, it's more dramatic than writing 1, 2, 3. But see what's happening. So one thing you can notice is that the way I wrote it is counterclockwise, and it's still counterclockwise. All of these are going to be counterclockwise because I never flipped my. Not that I did this actually. What's your name?
Oh, my name's Heather. I flipped it and then I realized I was messing everything up.
Oh yeah. So flipping is not a good idea for the scaling triangle. Yeah. So.
Parallel lines.
Yeah. What about parallel lines? So check out. We have lots of parallel lines. Like take these two. And note it. So this line is parallel to this line.
I did flip it.
Oh,
I
you have
flipped it
to-
over,
oh.
and then you shouldn't though, because when I flipped it, I messed everything up.
So this one is without flipping?
Oh no, this one is not.
There's no flipping here.
This one was smarter than
There's
I
a
was.
rotation
No, I
point
just was
around the
careful.
middle of each side.
Yeah. So one way to create this tessellation is take the midpoint. Let's say this was my original triangle. Take the midpoint of each side, rotate 180 degrees. And keep doing that, you'll get the whole picture. So that's why it's a rotation, not a flip. But okay, so these lines are parallel. Somebody said parallel lines. Cut by this transversal. And this angle has to equal this angle because we use the same shape in the template. So corresponding angles are equal. What about alternate interior angles, vertical angles, right? So this is like infinitely more fun and interesting than saying, today we're going to learn that, any of these things, because the kids can find those things without too much help, with some hinting, and many of these things without saying anything. And so you can dispose of some of these early geometry activities in a way that's kind of engaging and interesting, as opposed to a way that the kids are sitting there thinking, "Why is she telling us this?" So anyway, so this is a little pedagogical parentheses here, and now further evidence that I have no life. So that's that same tessellation. Okay, quadrilateral. Do some choose a quadrilateral different from your neighbors and tile with it. And again, don't do a square.
I know.
If you're going to do a square, do something unexpected with it.
I'll do this one. Yeah.
What do you do? I'm doing this.
This one might work. This one might work.
Is there a restriction that each vertex should
Well, the only way is either flipping or rotating.
Not right now. We're going to get to the more constraints in a bit. Yeah, totally general quadrilateral. Yeah, so if you want a challenge, pick the most general quadrilateral. If you want something easier, pick a special quadrilateral, like, you know, and see how it goes.
I'm trying to challenge myself. Well, that's one that's all four different.
Should they go yeah. This one's actually not much better. Try the kite because I'm going to try the kite.
It's a good time. So it really isn't, if you pick something on four different sides, you don't have much thinking to do because you only have one choice. We have two. If you don't do that, you have one.
And it works.
Yeah.
Yeah, continue it in this direction just to be sure, because clearly this is going to work. So just go one more level in this direction. Oh, which one? So here, can I borrow this?
Sure.
And as it turns out, again, I'm doing this faster than I would at school, but we'll tile. No flipping. Same method works. Same method works. To get adjacent ones, just rotate 180 degrees around the midpoints, and that will propagate correctly. The one that is usually frustrating is I often have students, for example, take the kite and go around the point. That's not going to work. The one thing that is sure to work is this method, but it's not it's not necessarily obvious. For most symmetric shapes, you can get many tilings. For a general quadrilateral, that's pretty much it. So, okay, we're gonna forge ahead. So. Okay, and so here's one with the general quadrilateral. So again, any quadrilateral will do.
It was almost easier to pick one that was a general quadrilateral.
Oh yeah, explain that.
Because you only have one choice. You got to match the side lengths. So if you pick a kite, you got more choices.
Yeah, it's easier to tile with the general quadrilateral, it turns out, because the next space, is going to, the shortest side is going to have to go with the shortest side. So then it's, do you flip it or not? And if you don't flip it, you've made it. If you just rotate it. Yeah.
With a kite, you can? Sorry.
You can do it with any of them. But just, you follow that method of rotating around the midpoint.
See,
Yeah.
in a kite, you've got two equal lengths, and you have to make sure you don't match them up.
Incorrectly,
equal
but
length.
it may not make a difference. But the advantage of the general quadrilateral is every step is forced.
Is it true that if you flip it, it will not work?
With the general quadrilateral, yes, it will not work. I mean, it's the same thing that I mean, by the way, I should switch back. It's the same business as we had in terms of analyzing the angles. So this angle here, let's call this angle. All four angles are represented at a vertex, and the angles in a quadrilateral conveniently add up to 360 degrees. So really, the only way to do this is to have all four angles represented, in a general quadrilateral case, and from there you can just translate that set of four, and it'll work because let's see, this angle 1 is here. This angle 2 is here, 4 is here. So at this vertex, we already have angle 2 translated from here. And then, let's see. Oh, no, wait, I have it. No, that's wrong. Okay, let me get this right. 1 is from here. Where does this one come from? Comes from here. Is it? Now I'm confused. This is 4 here?
Well, the one that.
Oh, this one is 4. Yeah, that one is 4 because I did that rotation from here to here. So, and then, so this must be 2 because of this. This is 2 right here because of this rotation. So, anyway, interesting stuff to discuss. And with things that have more symmetry, there are more tilings possible. For example, if you have 2 stripes, you can slide them until you have a lot of solutions from when any stripe solution. And so, which quadrilateral? Here's a good question for students to investigate. Which types of quadrilaterals will give us a stripe with like a straight line on either side? That's a worthwhile thing to discuss and think about. Okay, so now you're going to tile with pattern blocks and see if you can do a tiling. You can use any blocks you want and use the physical blocks. You don't have to draw anything. See if you can do a tiling where that clearly will expand forever. I mean, pattern blocks are great in that you can combine them in lots of ways, in lots of random ways. But do it with a pattern so you'll know your pattern will expand. So don't use too many blocks and organize them in some kind of systematic way. Yeah. So that's one. Okay, so the hexagons. But see, that could be the starting place. So let's say you have a bunch of hexagons, and so this is going to go on forever. Right. But now you can say, well, I'm going to replace this one, let's say, with 2 of these, or with some combination, like like this or like this.
Yeah, create some diversity. Yeah.
And then spread that around. Okay, great. So then there would be one of these over here, but then with a. Maybe I should have constrained this a little more. This is turning out to be hard. Oh no, there's one that'll work. So that's great. Now, figure out what's the next row, because now we know how you're going to go this way.
Yeah,
So how are you going to go that way?
this way?
Yeah, or towards
Or
it.
this way?
Yeah.
Yeah, I was.
Yeah. So how's this
I
going?
can't do it now. I
No?
can go on.
No. Well, let's see.
Not able to. I thought I had it.
No.
I thought I had it.
Yeah, I think so too. Because if your pattern extends, then every
Yeah, this will work. Yeah, this will work. Yeah, this will work. Yeah, this will work.
yeah, it's working.
Just use up a lot.
Okay, we're starting to get a bunch of successful tilings here.
A bunch of things.
What's your first shape?
Okay, I don't have any little ones available, but I like this
So your starting shape is one, two, one.
again.
Is this your starting shape?
No, this is mine.
You can just pick this and then you pick the
Oh,
I wonder if this
If it does,
would
it's
go
gonna be-
here.
I don't know if I can.
You know, this should be the beginning of your next
Maybe the
one.
size something like this.
Yeah,
Because you have,
I'm gonna.
you have a two, and
gonna
a
fit-
one and two.
I'm gonna.
Oh, it may still work. Probably still work.
I'm gonna.
Yeah, it will work.
and the
I think it works. I think it works. Because it's
Yeah,
one,
yeah.
one is symmetric.
Okay.
Yeah.
But will that tile?
I
mean, the color is-
change?
One,
I
two,
don't know, I really like it. I think it's cute.
So a less ambitious thing, you know, in terms of the math, but artistically great, is to go in one dimension, and you know, and so we have some really good patterns that repeat in one dimension. If they have straight edges, they can be piled, you know, next to each other. But if they don't,
How about this entire chunk if I can repeat, right?
yeah. So this will definitely go in both dimensions. You know, it'll fit kind of in, you know.
Yeah, take a picture.
Yeah. Oh, look, and these cubes.
Yeah. Oh my God, it's crazy. Yeah, we can. Welcome. And I like your title. Oh yeah. Bumblebee?
Yeah, and it's 2 weeks.
Oh, okay.
If I did this,
See it. Okay, I'm gonna go with the flow on that.
Okay, well, we're running short on time.
triangle shape there.
Oh,
There was a way to.
I was surrounding this guy.
Okay, so
Well, I'm going to borrow this one. See if I can successfully. I'm going to take the 2 pieces of paper and hope for the best.
So
yeah,
and then every green one is
if it's a tiling, don't you start with a shape and then
oh,
repeats the
okay,
same tile?
okay. Oh, I cannot say that.
I don't know.
Oh, okay, okay.
I can
little
say
more
that.
time
I
on
don't
the clock,
know.
okay.
Let's see. Maybe you can think about it as some type of unit, right? What is the repeating unit?
Yeah,
I can think about this guy maybe. Maybe something like
maybe
this.
like 1/3 of that.
Then
One,
you see my fingers there?
yeah.
Maybe including this guy. This guy including this.
So you
So
lay
here's a pattern that is going to be able to go on forever. Surround each hexagon with triangles and each triangle with hexagons. And this is an example of an Archimedean tiling where every vertex is the same. So for an Archimedean tiling, this one could be called 3, 6, 3, 6 because an Archimedean tiling is all regular polygons. So triangle, hexagon, triangle, hexagon. And let's see if we can bring some other ones up here to show. Oops. I know it looks like cubes. So yeah, it'll be easier. She has it much bigger. Can you bring this up, you think? So do you think this will travel? Of course. Okay, so here's one. You see the 3D-ness of it? And then here's another one. So, to know whether something actually will tile, we sort of want to convince ourselves that it'll go kind of in 2 dimensions. So clearly this is going to keep going this way. And what about this way?
Actually, isn't that leftmost edge? It needs to be flipped. That's one of the.
Yeah, see, this one needs to be like this, because we're just translating up. Okay, now it'll work. and if you just follow this, we have a little staircase effect as well. So do we have do we have other tilings to share? Oh, do you think this can be passed? No, I'll just walk around. Here you go. Okay. Yeah, do we get Heather's? Heather has an amazing one. It may not be possible. Maybe not. Did you take a photo at least? Oh. Is this yours? Okay, one last tiling. Is this great or what? And notice how the pattern this way is the same as the pattern that way. Right? So tan, 2 greens, orange, 2 greens, tan, 2 greens, orange, and so on. So, but yeah, they don't make bathroom tiles this way. Okay. Well, we have about 15 minutes until the food. And let's see how much of my remaining topics I can share. Oh yeah, I'll show you that. So yeah, here's that cube one. So I wonder if we could show yours, but so so on here you have a lot of regular polygons, and it's possible to, Archimedean tilings are tilings where every tile is a regular polygon, every vertex is the same, and they're edge to edge. They're not, you don't slide them over. Everything is a whole edge to a whole edge. So those are kind of fun. You can find all of them. There's not, I forget how many there are. Anybody knows? Like maybe 11 or something. And you can find all of them by experimenting with this and figuring, it helps to some extent to figure out what angles need to go together. And that would be great, yeah, but how?
Right here.
Oh, there we go. That's smart. I should have thought of that. Okay. So, hang on.
This one doesn't turn off.
So that's an Archimedean tiling because if you look at any vertex, it's a hexagon, square, triangle, square. Over here, hexagon, square, triangle, square. Any of the vertices are the same. Oh, unfortunately, the color is not showing up as well here as it is on the actual photo. Was this better? Oh. No, there it is. Anyway, so we could hunt for these, but whoops, I'm sorry. Walking away with your phone. So for example, this is a one that we already saw earlier, 3, 6, 3, 6. That's the a basic Archimedean tiling. Triangle at a vertex. Triangle, hexagon, triangle, hexagon. It's a good way to keep track. So if you do the activity with your students of finding Archimedean tilings, then it's a good way to keep track of which ones we found and so on. Okay. So now you are the guinea pigs for an activity I haven't done in decades. I did this with elementary school students many years ago and found it when preparing for this talk. Let me explain it up here, and then I'll give you some sheets to do it on. So this combines. Remember, we talked a little bit about tiling, and before that we talked a little bit about symmetry. So here's kind of a combination of the two. Let's say I started with these blocks. And then these are mirror lines, lines of reflection. So you have to look because you're going to be doing it in a minute. So I reflected the square in that line. Now I'm going to reflect in that line. Now I'm going to reflect in that line. Now I'm going to reflect this in this line. So the idea is not to be creative, but to only do reflections in the given lines. Reflection of the given pattern blocks in the given lines. And so I'm going to give you these papers. No, I'm going to give you some lines and some blocks. I mean, some, a starting design. And unfortunately, I only have 5 of these, but those are helpful to figure out. They're you can see reflections in them, so you can see where So oh yeah, that's the point. Yeah, I didn't think through about how to hand these out. Some people, I tell you what, if you get a pattern that's too complicated, trade with somebody who has a pattern that's too easy. They are the same. You guys want a different one? Here, I'm going to give you. Did the Xerox thing work out? Oh, good. Yeah. No, they're never a choice. Now there's reflect this. I mean, there's choice of where to go, yeah. So now he reflected here, but it's always you choose a block and choose a line and reflect.
My eyes.
You're in the optical illusion.
Yeah.
Okay, so I'm trying to line it up with that.
Yeah. Blue, so it'll be red there, red. Right.
There's lots of them. Yeah.
I will just do this one.
If you are brave. So which block are you reflecting?
I was going to reflect
This one in this mirror?
Yeah.
Because in this mirror it'll just be itself.
Yeah.
So it reflects in this mirror.
So that,
Yeah, that's why.
that goes there.
Yeah, because it has to be the same distance.
Okay. In that case, this one goes here.
So what's the block and what's the mirror?
This is the block.
Oh, and this is the mirror. Okay, yeah, this looks right. This is perverse. I have no idea. I can't remember how hard this was because I haven't done it in years. Yeah, yeah, that's good. I'm gonna push this a little in. Okay, keep going.
But they're not.
This would be a red.
So just choose a block and a mirror. So let's you're doing a blue. So let's say you're reflecting this blue in this mirror. Where would it end up? Yeah, that's right. No, it has to be the same. This is the mirror, so it has to be the same distance from the mirror on the other side.
I don't know.
Okay, so this is the original, and it's looking at itself in this mirror.
So it would be over here. Wouldn't
Yeah, yeah, yeah. No, don't move. The orange was right, but you're in the right area now.
it? Or would it be here? But it would be too.
No, it's looking at itself. It's looking at
right-
itself in this mirror.
It's right here. No.
So, yeah,
No, wait.
yeah, yeah. That's
This
it. That's
one
it. That's
would go
exactly right.
here,
That's exactly right.
this would go right there.
So do you see how?
And
See how these? Here's the mirror. They're kind of in the same position, but on opposite sides.
Oh, okay. But this is also a mirror?
Yeah, there are 4 mirrors. Okay, yeah, this is right. So now, and one way that might help is to put this like this and look in it. So you won't be able to see, but she will. Where would, do you see where this square should be once you reflect it in this mirror? And now, let's say you're going to reflect this blue one.
we'll reflect that one right over there.
So how far would it have to go? Or maybe this one, maybe. Where would it go? Can you see its reflection?
Yeah. It would be this one that's already there.
No, look in the mirror.
It would be here?
Look at the one I'm pointing to.
Oh, yeah.
It would be.
Oh, yeah.
Or even this
No.
one is easier. Where's the reflection of this one? Do you see where do you see in the mirror the point where I'm pointing?
Right. This is this one.
Do you have one? Oh, this
Wouldn't it?
one. This one.
Oh wait, where are the other ones? Let me give you another sheet. I have. Where are the leftover sheets? Oh, they must be back there. Can I take one of these?
Yes.
Oh, these? Here, try this. So is this working out?
I think so. Yeah. But it wasn't the pattern that I expected it would be.
Good.
I didn't expect that there would be 4 orange squares all together. From looking at the original thing.
Oh, well, but this mirror, I guess, made it happen, right? These two became those two. Oh, do you guys have the same one? Yeah, yeah. If you want a different one, or if you feel you're done with this one, I'll give you a different one.
Okay, let's try a different one.
Okay. Choose. Okay, that's a killer one. Oh, do you want a different one? Choose. Well, she took this one, so choose between these two.
this goes here, right?
Right.
We do not have another one.
Another blue?
I followed this as my
Uh,
read the whole thing. But these two blocks were already
Where the reflection of this one in this mirror.
Okay,
this
let's
was
put the
reflected
mirror
about
on.
this.
Okay, but now reflect this in this mirror.
Yeah.
Let- let-
Okay.
Which did you put it?
About this.
Yeah.
Okay, so here's the mirror.
There. Right.
So it would be reflected this one right here. Then,
Okay, so it's then it goes like this.
And now you can reflect this about this,
If it's reflecting that one, yeah.
yeah.
which has
Two
triangle.
oranges right here.
So first of all, let's put a triangle. So this triangle goes right here. Okay.
Oh, do you want a different one?
Yeah.
Yeah, that's
Can
it.
I get one without, which is not parallel mirror?
Yes.
Thank you. I'm wondering how this works in terms of.
Yeah, parallel mirrors you get. It's it translates.
So how? So all this has no contradiction. It's not going to run.
It
into
no. Well, if I remember right, like I said, this is many years since I made this, but it should work.
It should work.
Oh yeah, there you're getting it totally now.
We don't believe our eyes.
Yeah, once you get going.
Yeah. If we can't believe our eyes, we have to do it.
By logic.
Yeah.
He asked me if this was going to keep working, but so far so good.
More lines in here, it might be easier, but
Yeah, so one strategy is to reflect the mirrors themselves and draw the extra lines. Oh, do you want a mirror? Oh, okay. Some of these materials, the pattern blocks themselves, you can get lots of places. Almost every company that sells math materials will sell pattern blocks. So those are easy to find. Don't get the foam ones because they're not cut accurately. You can get them in wood or plastic. That's what I would recommend. But anyway, this is my website. And if you want to get the handout, print out the handouts, if you go to my talks, see there's a little talk balloon here. If you go there and find pattern blocks, these are links to everything we've done and everything we didn't get to. And so the website is math education page. And then within the website is the Geometry Labs book, which you can download in its entirety or one section at a time, and a link to where you can get that template, which is, as far as I know, the only one that allows you to do the Archimedean tilings. And so anyway, it's matheducationpage.org. So, okay, well, that's all for now. We didn't get to pattern block algebra another time. The last handout is what we didn't get to, and it's algebra.